Hi everybody. Today we're going to have a short lesson on open and closed pipes and how to figure out frequencies and wavelengths. And I'm going to start with a little demonstration, just something I had around the kitchen, which is a straw. And I'll show you that I can blow on over this straw and make a note. But if I cover the bottom of it, the note changes. Hopefully you can hear the difference in the pitch. When the bottom is not covered, I get this pitch. And when it's covered, I get this. That's an octave. Okay, so now let's talk about why that is. Okay, so we're going to start with this. So first of all, okay, so I just want to remind you that sound is a longitudinal wave. It's a compression wave. So usually, compression wave, it doesn't really look transverse like this wave here, but we draw it as a transverse wave in order to model the areas of high change in pressure and no change in pressure. So the nodes where it's not moving up and down is modeling places where the pressure is not changing, and the antinodes where it's moving the most is modeling places where the pressure is changing a lot. When there's a closed end, the pressure is not changing at that location. That's always a node. And when there's an open end, that's always an antinode because you can have big changes in pressure. Okay, so we're modeling this compression longitudinal wave. We're going to be modeling it as a transverse wave. And when we draw waves in pipes, we're really talking about a longitudinal wave, but we're going to draw it this way. All right, so here's a wave in a closed pipe. Closed means closed on one end. So there's only one end that's closed here. It's this right end, and then this one here, and then this other end is open. But this is a closed pipe. Okay, so again, this is modeling what we call a closed pipe. This was when I put my finger over one end. If you think about me closing both ends, that's not going to make any sound at all, right? So the closed pipe is when just one end is closed. All right, so let's look at some closed pipes. We've got three possibilities here. The first one is where the wave has a node at the bottom and an antinode at the top. This is the simplest way a wave can sit in here. And this is like half of a loop. Like this would be a full loop right here. And that's just half of a loop. This is the next most complicated way that you could possibly have a wave in this pipe. There's, instead of one node, there are two nodes. And then here's the next most complicated way. So this is what's called the fundamental or the first resonant frequency. This is the next harmonic and the next harmonic. This one right here, so now we're going to analyze what the wavelength is for each of these possible resonating frequencies. And by the way, what this is saying is that in the same pipe, you can get different pitches depending on how hard you blow the pipe. And I can't do it with a straw, but with a trumpet or a bugle, if you blow harder, you get a higher pitch. And I also have a whirly in the classroom where you spin it around, and if you spin it faster, you're going to get a higher pitch. Okay, so let's analyze this. Okay, so I mentioned that this first harmonic, or the fundamental, has half of a loop. I call half of a loop, I call these loops, I'm going to call them lemons. Doesn't this look like a lemon, right? This looks like a lemon and a half. And this looks like 1, 2, 2.5 lemons, right? So a loop is a lemon. And so this right here, this is a quarter lemon. And how many lemons make a full wavelength? Well, I can see a full wavelength here because this goes up, back, down, and back. That's a full wavelength. So 2 loops, or 4 half lemons, 1, 2, 3, 4, makes a wavelength. So this is a quarter wavelength on this fundamental, which means the whole length of the pipe is only a quarter wavelength. And the rest of the wavelength would be outside the pipe if you're going to get the full wavelength. In other words, if the length is a quarter of the wavelength is 4 times the length, or 4 meters. This is a 1 meter long pipe. For this one, in the second, oh boy, I shouldn't call this F1, F2, F3. I should call this F1, F3, and F5, and I'll tell you why that is later. But for now, we'll just say this is the second mode of vibration, so okay, you could call it F2. That's a little confusing. All right, anyways, going on. So this one has 1, 2, 3 half lemons, which means that the length is 3/4 of a wavelength, because a wavelength is 4 half lemons. And so the wavelength is 4L/3, or 1.3 meters. This one here, third harmonic, is 5/4 of a wavelength. So the wavelength is 4L/5, or 0.8 meters. And then when you want to find the frequencies of these modes of vibration, the first mode we're talking about is well, V equals F lambda, very furry lambda. So F equals V over lambda. V, speed of sound in air, and then in this pipe is 343 meters per second. So it's 343 over 4 times 1. 86 hertz is the fundamental frequency. And then the next frequency, which should actually, to be correct, would be F3. That's a correction. If you calculate it from the wavelength we got before, it's going to be 257 hertz. And the next one is going to be, calculating from this wavelength, is going to be 429 hertz. And so those are the first 3 modes of vibration of this pipe. Now let's look at an open pipe. Okay, here's the same question but with an open pipe. You can see these pipes have 2 open ends. This is like me blowing on the straw without putting my finger on it. And this is the simplest way you can have a wave in there. This is the next most complex way, and this is the third most complex way. This has 1 node, 2 antinodes. This has 2 nodes, 3 antinodes. And this has 3 nodes, 4 antinodes. 1, 2, 3, 4. Okay, so looking at the open pipes example, the length of the pipe is still 1 meter, but this is now not the last example. It was a quarter lemon here. Sorry, a half lemon, or a quarter wavelength. But this is 2 half lemons, and which means it's a half a wavelength. So L equals half of a wavelength, or wavelength divided by 2. In other words, the wavelength is 2 times that length. To make a full wave length, you've got to go, this is going to go down, down, up, up, and that would be a full wavelength. 4 half lemons makes a full wavelength, or 2 full lemons. All right, on the second example, this is 1, 2, 3, 4 half lemons. That's a full wavelength right there. That is a full wavelength. So the wavelength is 1 meter, or the length of the pipe. And then when we look at this next one, this is 1, 2, 3, 4, 5, 6 half lemons. So the length is 6/4 of a wavelength, or 3 halves, and therefore the wavelength is 2 times the length, 2/3 of the length. And so the wavelength is 0.67 meters. So now you have the wavelength for each of these. Now you can calculate the frequency. And this is a general strategy for solving this kind of problem. You need to figure out the wavelength in that pipe first, and then you can plug that into the V equals F lambda equation, solve for F, and get the frequency. So the fundamental frequency, 172, the next harmonic, 343, and the next one, 514. And what I want you to notice here is that F2, the second harmonic here, is double the first. The third harmonic is 3 times the first, right? That's why for an open pipe, they are called F1, F2, F3 because they're multiplied that way. But for a closed pipe, they're not. F2 is actually 3 times the fundamental, and F3 is actually, this is 5 times the fundamental. So the actual way that we number these is F1, F3, F5 to reflect that idea, to show that fact about it. Okay, so now I want you to go to the assignment sheet for this class and click on this resonating frequencies and harmonics worksheet, and see if you can solve this with variables. So it's just like the example I just did with numbers, but I want you to do it with variables. Using the variable pipe length is L, and find the first harmonic, second harmonic, third harmonic for the open pipe. Do it for the closed pipe, and I want you to find a pattern for the nth harmonic. And you may already have a sense of what that is, but do that, and then do it again for strings. For a string, you're going to have nodes at both ends. Think of a jump rope for the fundamental. So you're going to have a loop, one loop, like that, it's kind of like that for the fundamental. You can draw the loop above, and you can also draw it below. You can just draw both. And then the second harmonic will have a node in the middle. So you have a loop, loop, 2 loops like that, and you can draw it below as well. So you'll do that for open and closed pipes and for strings, and for each one you'll find a general pattern, and then you can check your answers in the solutions on the web page. Okay, so the last thing I want to do is answer that first question, which was, why do we have an octave? Why is the closed pipe an octave lower than the open pipe? And if you look at the frequency for the closed pipe, it's 86 hertz, fundamental frequency. If you look at the fundamental frequency for the open pipe, it's 172, which is twice 86. So it's a higher frequency for the open pipe, and it's actually twice the frequency of the closed pipe. The open pipe is twice the frequency of the closed pipe, and twice the frequency is an octave higher. That's what an octave is. It's twice the frequency, and that's always true. If you double the frequency, you're going to go up by an octave. So that's why we hear that octave difference. That's the mathematical reason. Okay, and that's the end of these notes. Do the worksheet and then check your answers on the solutions posted on the website.